Alright, so here we have Chapter 13 homework. We have parts A and B here. I believe parts A are problems 1 through 7, and then 8 through 12 is the start of B, which is the momentum part of it. So first we have the energy, or conservation of energy. So problem number 1, we have an ore operating, or an ore mixing operation. We have a ore or piece of something hanging by a rope, moving this far, and it's all moving as one whole system that way until it stops up here, and the ore will swing, and it will be a certain length away, but it will go up a certain height. And we are looking for, we're given an initial speed of 10 feet per second. Max, we're looking for the distance that it will cover, but we can find that using conservation of energy and work done. So we have the initial energy. We know that the final energy is equal to 0, so the work done is all vertical to slow it down. And so we know that it's 1/2 mv squared minus mgh equals 0. Bit of algebra, cross out the mass, cancels out, and you get h is equal to velocity squared over 2g, which is equal to 1.55 feet. And we know that d is equal to, d squared is equal to the length squared, and the length minus h that we just figured out. So again, we have all those variables, so d equals the square root of 30 squared, or the length squared, minus the length minus height squared, and we get that d is equal to 9.53 feet. Final answer. Question number 2, we have a trailer truck, enters a 2% uphill grade, traveling 72 kilometers an hour. That is equal to 20 meters per second, and then the final speed, it reaches 108 kilometers per hour, which is 30 meters per second, and we know it reaches that in 300 meters. The cab has a mass of 1,800 kilograms and the trailer 5,400 kilograms. We're looking for the average force at the wheels of the cab and the average force in the coupling between the cab and the trailer. So the coupling is just this area where the cab and the trailer meet. So here we know that the truck travels a total of 300 meters of work being done. And then the 2% grade means that every 100 meters it goes up 2 meters. So over the course of 300 meters it goes up 6 meters. And then we know that the total distance that the work is being done is over 300 meters. And so we have initial velocity, work being done, and final velocity. And we know that the work being done is gravity's doing work, which is just mass times gravity times the height difference. And then we also know that there's the force of the truck over the distance. So we know that kinetic energy is equal to the 1/2 mv squared, and we have that on both sides. We have the initial velocity, final velocity, change in height, and the distance traveled. So using that, we just plug in, do a bit of algebra, and we find that the force of the truck is 7,412.6 newtons. And then for part B, what the trailer feels is, if we get to do a free body diagram, actually, what the trailer feels is, well, it's got its weight slightly off, and then, or its weight down, then its normal force slightly off center, and then it's got the coupling. And so no friction, no anything, so we know that the acceleration has to be that way. That's assuming the coupling is in tension. Pulling it up, if it was slowing down, the coupling would probably be pushing it that way, but since it's accelerating, it's probably pulling it that way. And so it's just the mass of the trailer and the coupling acting on it. So we have the initial kinetic energy of the trailer and the force of the coupling over the distance. The same thing as the other problem, but the masses change. And again, we do end up doing the same algebra. We know all of this and the distance traveled, and we get that the force of the coupling is 5,559.5 newtons. And yeah, I mean, you could also find it, I guess, if you're just looking for the truck as well, but it'd just be the opposite of that, because if it's in tension, it'd be pulling away from the side, but that doesn't really matter. Then we're doing another similar problem here. Subway train traveling at a speed of 30 miles an hour. Brakes are fully applied on the wheels of car A, which are there, causing it to slide on the track. Not applied on the wheels of cars C or B, knowing that the coefficient of kinetic friction is 0.35 between the wheels and the track, determine the distance required to bring the train to a stop. First we gotta do a little unit or conversion. Final velocity is equal to 0. 30 miles an hour is 44 feet per second. We know that the end velocity again is 0, so that means the energy is 0 at the end, so that means work has to be going out of the system. And we know that work out of the system is the force of the brakes times the distance. And so here I have a little free body diagram of car A, and we know that we have friction going that way, velocity is going that way, we have the normal force of A and the weight of A. And so we know that the force of the brakes is equal to force of friction, which is equal to the normal force of A times the mu, which is the mass times gravity times mu, or just the weight. And so anyways, sub that into there, and we do a little algebra again, and we get that D is equal to 279.1 feet until it stops. And then for part B, we're looking for the force in each coupling, so we'll do that in two parts as well. So for part A, if it's stopping, we know that the force of brakes goes that way. We know that the coupling is probably pushing it that way because the mass behind it wants to keep going that way. So, or I guess you could say it's over here and that it's in compression, because it is. And we know that the work being done is the brakes and then also the force of the coupling times distance. And again, we already know the force of the brakes, and we know that the final energy is equal to 0. So we get our initial kinetic, which is just the mass of car A, I believe. And that, or kinetic energy, and then we're looking for the force of the coupling. We do some algebra, move some stuff around, and we get that the force of the coupling is equal to 19.4 kips in compression. So yeah, I drew that wrong there. I believe so. Yeah. Then it's important to note a kip is equal to 1,000 pounds. And then for the coupling between B and C, we're assuming somehow car C needs to be stopping. So the force is the coupling pushing into it. Again, in compression to slow it down, then no friction. normal force, weight. So we know that the work being done on it is all force the coupling. So this is easy. Again, do some algebra, move that over to the right side. Plug in what we do know, and we can find the force of the coupling at BC is equal to 8.62 kips in compression. And problem number 4. Let's see. We have a sphere being released from up here. We're trying to find the theta at which it breaks. We know that once the force of tension is equal to 2 times of the mass, that means the string will break. So we'll start out with our initial work being done. So we know it starts out with V0, or initial velocity of 5 meters per second. We're looking for what V2 equals. And so we know that delta H is equal to L sine theta from across over there. And so that is the difference in height. And we know that looking at our diagram here, our force, this is our normal, that's our tangential. We know that everything in the normal direction is v squared over the radius of curvature. And we know that the radius of curvature is equal to L as well. So we're able to sum up the forces in the normal direction of the plane, which is force of tension, and the weight normal, which is just the weight times cosine theta. And so we put all those on the left, and again, do some algebra, sub in for what we do know, and we know that the final velocity squared is equal to 4g minus 2g sine theta. And so that means we were able to put that into there. Let me bring it down there, put stuff into, so we can sub it in there. And then, again, we're looking for sine theta here, so we need to get those two terms together. And do some algebra, some shifting around, and we get that theta is equal to 14 degrees exactly, or 14.00 degrees, and that's when the rope breaks. Question number 5, this one had me a little confused at first. I mean, check the answer key, but I was looking at it moves 75 meters per minute, but I guess that doesn't really matter. But again, we're looking at skiers per hour, which 1 hour is 3,600 seconds. And the lift is going up and weight down. So we know that force is equal to mg. And we know that power is equal to the force of the lift times distance over time. And we also know we have to know how many people it does that to as well. And it does 1,000 skiers at all weigh 70 kilograms at an average speed. That doesn't matter. So the average power required is, right? Yeah. So 1,000 times the mass, 1,000 skiers times the mass of each of them times gravity times distance divided by time, 57,225 watts. For max power, we have our 300% overload, so that gives us 4 times our average power is 228,900 watts. And then if our efficiency is at 85%, that's an M. Our max power required would be, again, 0.85 equals the output over the input. And so that means our input needs to be 269,294 watts. Then for problem number 6, the string, so we're looking for the speed at B and C of this collar here. We know that at C, the collar, or that the spring here is not stretched at all or compressed. So there's no energy there. That means that it's all in speed. But we know that at A, we have zero point 0.1 meters of, over here, we know that we have 0.1 meters stretched beyond, and we know that the potential energy of a spring is 1/2 kx squared, or k delta squared. And we can also find how far stretched it is at point B. And we know that no energy there, or kinetic energy there, it's all in potential or gravitational. So, that's mgh plus 1/2 k delta squared equals 1/2 mv squared plus 1/2 k delta b squared. So again, we know everything except for the velocity b, so we do some algebra, and we find that the velocity at b is equal to 2.48 meters per second, and then we do the exact same thing here. We can compare that, because of conservation of energy, we can compare the energy at A to the energy at point C. And so we know that, we know that C and A are at the same heights as each other. So the potential energy at A in terms of gravitational cancels out with the potential energy at C. And then, so that means that the spring energy at A has to equal, and we know that there's also no stretch or potential energy, spring energy at C as well. So we know that is 1/2 k delta A squared equals 1/2 mv squared. Again, we know everything besides the velocity. So we know that do a little bit of algebra, and the velocity at C equals 1.73 meters per second. And then at 7, so this is actually a pretty interesting problem. But here we have the package sliding down, initial velocity at 2 meters per second, weighs 50 kilograms, and sliding down, it's caught by these springs, or by the spring, and we know that the spring is already down 5 centimeters, or 0.05 meters. And so moving down 20-degree slope, it travels 8 meters, and we can put everything relative to this guy here, to that axis. And we know that there's, I guess I don't know, depending how we do it, but we know that as initial velocity, or initial kinetic energy, plus potential energy has to equal the potential energy in the spring, and also the potential energy as well, which is actually negative because it'll go below that point. But that is equal to, what is it? Mass times gravity times the distance traveled, or height traveled, which is equal to delta sine 20, because there. So, yeah. And then at this point, we have everything besides delta. And so we do a bit of algebra, and then, I used a calculator here, but we get that delta is equal to 0.269 meters, or negative, but it's not going to move up that way at all. It's moving this way. So we know that it's 0.269 meters. Now we move on to part B, or the momentum part of it, and we use this equation a lot. And it's important to note that momentum is equal to kilogram times meters per second. But problem number 8, we have steep safety ramps built besides highways to enable vehicles with bad brakes to stop. We have a 10-ton truck, which is equal to 20,000 pounds, or 20 kips. Ramp is 15 degrees, and we know the initial velocity is 108 feet per second, and it travels for 6 seconds before reaching 36 feet per second. We're looking for the magnitude of the braking force and also the additional time required for the truck to stop. So, free body diagram, our axis is going to be this way, so up 15 degrees, but we know that the force of the brakes is going down or backwards. Normal force, weight is kind of split up into two different things. So we have weight slowing it down that way, and also just going down, supporting it. So that's equal to the normal force. And we know velocity is going that way, but we know that its acceleration is that way. So we're looking for the force of the brake, and we know how long it takes everything to act, and we're kind of doing everything in the X direction here, because that is the way the velocity is also going. And so here we have, again, everything positive is that way, and then negative is that way. So force of the brake is working against it, causing the acceleration that way, and also the weight. And then this basically means the sum of all the forces times time is equal to the change in, or to the impulse, or change in momentum. So we have everything except for the braking force, and doing a bit of algebra, we find that the force of the brakes is equal to 2,277 pounds. And part B, the additional time required to stop. Now that we have the force of the brakes, use the same equation, but we have a delta T, and we do a bit of algebra, very similar but a little different, and we get that delta T is equal to 9 seconds, so it would take an additional 3 seconds of time to stop. And part 9, we have a system initially shown at rest, but then we had a 150 Newton constant force going to the left on the collar. No friction. Determine the time at which the velocity of the collar B will be 2.5 meters per second to the left, and the corresponding tension in the cable. So free body diagram B, we know that the acceleration is going in that way, the velocity is going in that way, and we know that the force is acting on it 150 newtons, and then we have two tension back because we have two cables on it, or one cable, which means that the tension is the same on both, but those are pulling it that way. And then we have a reference point X, which we're defining positive is that way, and then Y positive is that way with our geometric constraints. And then we have for total length, 2x plus y is a constant, but then you take the derivative, so 2 times vx plus y is equal to 0, and then the acceleration for both, or 2ax plus ay is equal to 0. So now the velocity of y is equal to 2vx. So we know that the sum of forces is equal to the change in momentum, and we know that initial momentum is equal to 0, so we're looking for how long it would take for the 8-pound mass to reach V1, which is 2.5, but we don't know the tension yet or the time. But we can use block A here, the 3 kilogram block, with only one set of tension up and weight down. We know that the relation is Vy equals 2Vx, which means that Vy is moving at 5 meters per second. And use the same thing, initially at rest, so it equals 0, or initial momentum equals 0, and that the T minus Wt, or T minus W, which is the sum of forces there, times the time is equal to the mVA1, which is equal to 3 kilograms times 5 meters per second. And so we're able to get that the tension is equal to 15 plus 29.43 T divided by T, which is equal to 15T, 15 over T plus 29.43, which is there. And then we're able to sub that in for tension. And then once we sub that in here for tension, we do some algebra and we're able to find the total time, which is 0.549 seconds. And once we have that, we can sub that into our tension equation right there. And we get that the tension is equal to 56.8 newtons. Problem number 10. We have another impulse momentum equation. So we have initial velocity coming in, or initial momentum coming in, a bullet with a velocity coming in, and we know that momentum is conserved, assuming it's all direct impact and such, or at least I just assume momentum was conserved. So we know that ma, initial velocity, is equal to the total mass and the velocity afterwards. So, 1 kilogram block, 6 gram bullet, length is 2.2 meters. Trying to see the initial speed of the bullet, and we know that the final theta is equal to 60 degrees. So we're able to find a height, or change in height, or change in potential energy. And then we're looking for the impulse imparted by the bullet on the block, and then the force of the cord immediately after impact. But using that, we know that our initial energy equation coming in is that we know that right after the collision, our kinetic energy has to be equal to the final potential energy. And we know that H is equal to the length minus the length cosine theta. And up here, do some algebra, it's 1/2 times the total mass times velocity squared is equal to the total mass times g times h. Masses cancel. Do some algebra. Initial velocity equals the square root of 2 times gravity times height. And we get that V1 equals 4.646 meters per second. And then we bring in our momentum equation from over here. And we know that the initial velocity to have the same momentum as the final must have been 778.9 meters per second. And then we know that the impulse on the block, or of the block, initial velocity equals 0. We know that the velocity after, and then the sum of the forces, this is what we're looking for. And we know that the velocity after is equal to 4.646 meters per second, and the mass is equal to 1. The thing says joules on there, but I don't think that's right for the answer key. But that means that we know that the impulse is equal to 4.646 kilograms times meters per second. And then for 6, after everything is combined and the blocks and both are moving together, masses are combined, and that is accelerating in the, and why did that? V is actually equal, that's V tangent, and that's a normal. But the normal acceleration is going up to the center. It's always pulling on it no matter what. So we know that the tangential acceleration is equal to velocity squared over the instantaneous curvature and sum of the forces, T minus the total weight. And so we know that T equals the total mass times velocity squared over the curvature plus the weight. And sub everything in because we know everything, and the tension equals 19.74 19.74 newtons. Number 11, I only did A and B. It's a little confusing, just try to think through it, but all balls of equal mass, does ball always stop, or does just hit off the center because it comes off? And I don't know how I'm doing it. Is would it like hit there ish, or how does it just like hits off center, but the center of masses line up somehow? But that's just more to learn. But we know momentum is conserved no matter what. All masses are equal. Simulated chords. We have E, coefficient of restitution. We have inertial velocity, and for A and B, we just work with variables. We don't have any actual hard numbers, but we're looking for velocities of A and B after the first collision, and then the velocities of B and C after the second collision. And so we know that initial velocity or energy B is equal to 0, and we know that, so we just take that out of there. And we also know that the masses are all equal, so we know that the velocity of A is equal to the velocity prime of A, and then plus the velocity prime of B after, so that's over here. So and we also have the equation VB prime minus VA prime is equal to E times VA minus VB. So we know from the before, VA prime, or we can do some algebra, VA prime is equal to VA minus VB, because we are given, I'm assuming we have VA at some point. And so we also know that VB is equal to 0, so we can take that out, and we sub in VA minus VB prime for VA prime. Do some algebra, we get 2VB prime is equal to E times VA plus VA, so we get that VB prime is equal to VA times E plus 1 divided by 2. It matches the answer key, and then once we know VB prime, we plug in to this equation here, I believe, and we get VA prime is equal to VA minus VA times E plus 1 divided by 2, and then after some more algebra, we get that VA prime is equal to VA times 1 minus E divided by 2. And for part B, again, masses cancel, but we have mVB prime plus mVC, which VC is equal to 0, is equal to mVB double prime plus mVC prime. And so again, masses cancel, take all those out. And we also have the same equation as before. We know that VC equals 0, so we know we can do some rearranging, and we can also sub in for VB prime, and we can find VC prime with some more known variables and sub that in over there, which again over here, and do some algebra, and we find out that VB prime, double prime is equal to VA times E plus 1 divided by 4 times 1 minus E. And I actually did that twice, once by finding VC prime first and then plugging in, which I did over here, and I got the same answer as above, so I believe that would be correct. And then after finding VB double prime, I subbed into VC prime and got the same answer as on the answer key, actually. I actually never fully circled that. But yeah, subbed in VB double prime, did some more algebra, and yeah, I mean, BC prime is equal to VA times E plus 1 squared divided by 4. And that part does match the answer key, but not VB double prime. And for our final problem, we have a block coming in from this side, initial velocity, and then there's an impulse. Momentum is conserved. We know that the mass of A, or velocity of A, is originally 0, but mass of B does have velocity, so it does have momentum, and that is equal to the momentum afterwards of A times VA prime plus MB VB prime. So we can find a relation here. We know that the mass is of B, it doesn't change, but that is equal to 2 equals 0.5 VA prime plus VB prime. So VB prime is equal to 2 minus 0.5 VA prime. And then we have our other equation up here with restitution variable, or E. And from this, we know that VA is equal to VB prime plus E times VB. So we know these variables, or have substitutions for them, and we do some algebra. We get that VA prime is equal to 2.4 meters per second. Then we can sub it right back into that equation or that equation, and we get that VB prime is equal to 0.8 meters per second. And this part over here is just testing out if I switch the variables like here and here, like if VA was really VB and such, and I got the same answer. So that was just for curiosity. So for post-impacted ball, they're not together, but they have their own momentums now, or each have momentum now, and so it's just a conservation of energy. We know that all the kinetic energy of one is turned into potential energy, or of A is turned into potential energy of A. And so 1 half mv squared, or VA prime squared, is equal to ma times gravity times h, so masses cancel. And we know everything besides h, so we do some algebra, plug in for VA prime and gravity, and we get that h is equal to 0.294 meters. And then for B, we're looking for the distance traveled by the block. Sorry, for part A, we're looking for the maximum height reached by the sphere. And for free body diagram of B, we just have the normal force, the weight in the vertical directions, and then we have the force of friction going opposite the velocity. And so it doesn't have any potential energy at the beginning or the end, so we just take that out, and we know that it has 0 energy at the end, so that means work is done, and we know that work is equal to the force of friction times the distance, and we know that the friction is equal to the normal force times mu times distance, or just negative mu times mg times d. And so we put that on the right side, make it positive, and so we know that, masses cancel, but we know that 1 half VB prime squared is equal to mu times gravity times distance. So we have everything but the distance, and once we plug in, we find that the distance is equal to 0.054 meters.